Quantum theory doesn't just say it's random, it says it's random, and also in this particular experiment you will see this particular result exactly 3/4 of the time. Of course it is a pretty radical thing to kind of accept that there might be parallel worlds with different copies of you and experiencing different things. Can I come up with a compelling natural way to pick copies of me which recovers the right results? We just don't have a lot of good ways of thinking about what it would be like to live in a multiverse, a branching multiverse. I always want to understand things at the deepest level and trying to see what does this theory really tell us about the universe and our place in it. If the issue is you're treating measurements in a weird special way, stop treating them in a weird special way and see what happens.
Hello, welcome back to the Quantum Foundations podcast. In this episode, we're joined by Tony Short, who is a theoretical physicist at the University of Bristol.
Hi.
Thanks, Tony, for joining us today.
It's a pleasure.
So the topic we'll be talking about today is some work that Tony has done on deriving probability in the many worlds theory of quantum mechanics, which is one of the many different areas that Tony's done research on. So to start with, could you tell us a bit about how you became interested in doing work on quantum theory in general?
Yeah, so I think I was always interested in kind of understanding the fundamental laws of nature. That was my reason for getting into physics. And of course, when I went through my university degree, I discovered that at the lowest level at the moment, we think is quantum theory, describing the fundamental interactions of all the smallest things in nature. And so naturally, that was the area I kind of wanted to understand. And at the end of my undergrad, I carried on to a PhD and then carried on working in this area. So I think, just the desire to understand the fundamental laws of everything. Really.
Mm-hmm. Yeah, cool. And you've worked on several different areas of quantum physics. What kind of led you to looking at the many worlds interpretation?
Yeah, I think just obviously there is this big problem at the heart of quantum theory of we understand very well the mathematics of it, but it's controversial still about what it really says about the nature of reality, about how reality really is in light of this theorem that explains how things work. And so working on it is natural to sort of think about that, and I do think it's a really important problem. And it just seemed to me that the many worlds interpretation was kind of the simplest explanation of how this mathematical theory connects with the world around us, basically. So the idea behind it, maybe we'll go into some more detail later, but basically you take a very simple structure and you just sort of take quantum theory seriously. You kind of say, well, how do we know quantum theory works at the smaller scales? If we just take the usual assumption that the same rules that apply at the smaller scales just kind of keep applying all the way up, you sort of naturally get led into the many worlds interpretation. And I didn't see a particularly strong reason to not follow that approach. And in fact, it makes sort of the theory a bit simpler, in a way that we'll probably discuss a bit more later on.
Yeah, great. So what is the problem in quantum mechanics where why do we need the many worlds interpretation? Where does it come from?
Yeah, so basically in quantum theory, as you traditionally learn it as a sort of student, there are two different ways that a system can evolve. There's the sort of when you're not doing a measurement on a system, it evolves via the Schrödinger equation, which gives you a kind of smooth, continuous kind of evolution that's reversible and very sort of mathematically kind of beautiful. And that applies to almost everything, but there's when you do a measurement on a quantum system, you put that aside and apply a completely different set of rules. You say, when you do a measurement, you apply some sort of different machinery and you get an outcome of your measurement at random, and quantum theory tells you what probabilities you get the different outcomes in your experiment for. And on the face of it, that is quite unsatisfying because there doesn't seem to be a really strong distinction between measuring devices and everything else in the world. Like, measuring devices are made of atoms and they interact with things via normal forces, so it's completely inexplicable why you need a completely different rule for them as everything else. And that is essentially resolving this issue is what's called the measurement problem in quantum theory. And there are various different approaches, but the many worlds interpretation basically takes the view that you should focus on this first type of evolution where all everything else you use to model every other kind of interaction and evolution. So the Schrödinger equation, and it just says, suppose there was just the Schrödinger equation, there was no second set of rules at all, everything just evolved by the Schrödinger equation, including measuring devices, and you and everything in the universe. And if you just follow that to its logical conclusion, it basically leads you to the many worlds interpretation. So when you do that, when you just apply the Schrodinger equation to a thing which is a measurement, what you find is that the state of the universe sort of naturally branches into, it stays one complete quantum state, but it has within it parts in which you saw one result and a different part, equally real, in which you saw a different result. And that sort of branching structure, where different sort of copies of you in some sense see different results, is why we call it the many worlds interpretation. But it should be pointed out that the Schrodinger equation doesn't really know anything about worlds or branching or anything like that. It's just a very simple mathematical model, and this is more about the stories we tell about what it's like to live in a world that obeys that equation. So things like, a world or branching, these are kind of slightly fuzzy concepts that we're using to kind of talk about what this theory is predicting, but they don't appear in the axioms at all. They don't appear in the fundamental rules of the theory.
So the trying to solve the measurement problem of reconciling these two different types of dynamics that you get, the Schrodinger equation and then these other rules that apply for measurement devices. In trying to solve that, one approach is to say that it's all governed by the Schrodinger equation, and then there's this kind of many worlds interpretation of what that evolution means is that there are these multiple branches.
Yeah, if you just you just run the Schrodinger equation on something that looks like a measuring device interacting with the system, it will naturally give you this kind of branching structure. You don't have to put that in by hand as an extra thing, it just comes out, the mechanics. And
what are some of the problems with this approach? Why is the entire community not convinced?
Yeah, it's a good question.
Yet?
I mean, for me, it seems quite convincing. But I think the biggest problem it has really is just people find the idea of all these different branches quite unpalatable. So I think that honestly the biggest problem is people just don't like it.
Yeah.
Rather than any particular technical scientific problem. Like the idea that if you're doing quantum measurement and you think you've seen one result, you have to believe that there's another copy of you somewhere in the quantum state that sees the different result. That that feels something that's been covered, I guess, a lot in science fiction, but it feels very strange to say that that's really what's happening in our real world. But it is a very natural consequence of the sort of the mathematics of it, basically. And I think people also don't like it feels very extravagant having all these worlds. Like it seems like a big cost to have a lot of worlds. But in some sense, the way that quantum theory works, the whole state of the universe is still described by a single mathematical object that kind of contains within all these worlds. And that mathematical object is in some sense a bit like a vector, which is a bit strange because you think of them more as how things move in space, but it is like that. But in some sense, it's a very simple mathematical object, and it's only when we try and sort of understand what it says about the world that we kind of talk about it in terms of these branches and things like that. But actually, it is a sort of single entity in some sense, the quantum state of the universe, that is sort of just as simple if it has many branches as if it has just one, like in some sense. Mathematically, they're not really very different. So that's the one big problem, and I suspect that's the main problem why people don't like it, honestly. But there are a number of sort of more technical issues to kind of address. And the main one is, how do you, when we went to this path, when we looked at the many worlds interpretation, what we did was we dropped a complete set of rules for measurement. And the question is, can you get all those rules back from just the first part, from just the Schrodinger equation type evolution? And in particular, one of the biggest problems is the one that I was worried about and did some work on recently, which is how do you explain that quantum theory makes very precise predictions for the various probabilities that different measurement results will occur. Now, the issue with this is that in the many worlds interpretation and in the Schrodinger equation that governs its evolution, everything is kind of smooth and continuous and reversible, and crucially, there are no probabilities. It just evolves via some laws, and you get an initial state, goes to a final state, and it's all what we'd say deterministic. It doesn't have any randomness in it. And obviously, that's a bit of a problem if you're trying to recover probabilistic predictions for the theory. So on the one hand, it's you can get around this kind of conceptually reasonably easy, I think. So you suppose that this state comes in and it sort of branches into two branches, in a smooth way, where each branch, there's a copy of you that sees a definite measurement result. One of them sees like often you do these things with kind of measuring the spin of a particle, and it's either spinning up or down, say. So one copy of you sees that the spin was up, the other one sees that it was down in their measurement. And so that, you might think, well, if you took the experience of just one copy of you, each copy of you would only see one result, and you can understand why they don't directly kind of experience the other copy, like why these copies are kind of separated in some sense in a way that makes it hard for you to be directly aware of them. You could imagine that living in that structure, it might feel random because, you do an experiment and then each copy you sees a particular result, and it might feel that result was random because you're not directly aware of the other copy of you that saw the other one. And so when you're living in some sense on one branch of this branching structure, it kind of feels random as you kind of, and of course there are other copies of you living on the other branches. They're all equally real. But that you could sort of just about think, okay, that sort of makes sense, and I can see why it might feel random even though it's not. But you have to go a bit further than that, because quantum theory doesn't just say it's random, it says it's random, and also in this particular experiment you will see this particular result exactly 3/4 of the time. Or, okay, in a large number of trials you'll see roughly 3/4 of the time this result.
Yeah.
And that is a harder thing to get into the Schrödinger equation picture, because there are no probabilities directly, so you have to understand what exactly does that claim mean, and crucially, can I get back the same predictions that we have actually tested a lot in the lab? So we have tested the predictions that quantum theory makes about the probabilities, and it's been very successful. These rules for measurement work really well, and so we have to kind of explain why they work really well, and that means explaining where the probabilities come from. And that's the problem of probability. There are other problems. I guess the other main problem that people talk about is something called the preferred basis problem, which is about as I sort of said several times now, you kind of, the mathematical object is just really one single object that describes the whole state of the universe. And yet when we talk about it in many worlds, we often do sort of write it or talk about it in this sort of branch structure where you say, well, actually you could think about this single object as being kind of a sort of sum of different branches, each of which has various properties. And it seems like, because the exact way that you talk about what the worlds are and how exactly you want to branch that is not baked into the rules of the Schrödinger equation. So you might say, well, why are you picking to kind of describe it in terms of these set of worlds rather than some other set of worlds? How do you pick the way you talk about it in terms of these sets of worlds? And could you have picked a different way, and would you have got a different story? And so that is a sort of quite a subtle issue. I mean, there's sort of several answers to this. My view is that you should basically talk about it in a way that helps you understand it, because we still, everyone agrees on sort of the maths of it, so it's just a question of trying to understand what it means. And in that sense, as long as you're sort of breaking it down in terms of if you want to break it down to a set of worlds, each of those worlds you want to be able to sort of understand as a single entity. And so it makes sense for those worlds in each world for objects like people to have well-defined states, tables to be well-defined locations. So you kind of pick the worlds as things which you kind of classically understand, at least to some level. So they're kind of reasonably well-defined. And you also want them to be reasonably stable, so they don't just sort of immediately disintegrate. And these kind of, in some sense, it's sort of slightly fuzzy area. It doesn't really matter if you slightly change what you call the world and what not. You'll get the same predictions pretty much, as long as you just, do it in this sort of sensible way. So for me, it's more about what we pick, the ones we do, because they're useful for sort of telling stories about what it's like to live in this structure. But there's also this process called decoherence, which plays a part of this. So I talked a bit about these sort of things being sort of stable, and it's part of that. So there are certain ways you can describe the world which are kind of, in some sense they're kind of stable under evolution. They don't kind of immediately change, and the other thing is that typically when you talk about worlds, you always imagine it sort of branching outwards, and you typically don't want, when you call these things different worlds, you typically imagine that they don't then recombine and you get sort of interference between the worlds. And that is kind of a subtle point, but basically when we do normal quantum experiments on small things, we do actually see, in some sense, worlds kind of splitting up and coming back together and getting interference. So if you think about one of the most famous quantum experiments where you send a single particle at sort of 2 slits in the screen, and then on the other side of the screen, that single particle hits a detector, and it turns out where it hits the detector depends on both the slits, not just one of them. And it can reach some places and not reach other places, and the only way to understand this is to consider that in some sense the particle went through both slits. And of course, in a sort of many worlds picture, you say, well, perhaps there's sort of one world in which it went through one slit and one world in which it went through another, and then those two worlds kind of come back together at the detector and interfere with each other, and that can help explain what you see. But we don't generically experience this in our everyday lives. Typically and certainly in terms of the rules for measurement in quantum theory, once you've done the measurement, all the other possibilities kind of go away. And so in many worlds, you kind of also have to explain that phenomenon. Why is it that we don't see things coming back together all the time and constant interference? And we can effectively, when there's a measurement, think about the result we found and forget all the other possible results, which is in practice what we do when we do quantum measurements, and it seems to work. And I guess the main reason we think now that we can do that for big things and not for small things is that you only get interference between the worlds can only really come back together if everything in the universe comes back to the same state. So if you've left any trace anywhere in the universe of what you sort of some earlier time of where you were in this different world, then that'll stop you getting interference between the two different kind of possible paths through this set of universes. So in other words, you only get interference if everything, there's two possible sort of stories that come back to the same point where there's no trace left about which way you went. And for big things, they don't tend to do that because they do leave lots of trace in their environment. I mean, you can see me, so I'm obviously leaving a trace in the light somehow in this room. And it's, astronomically impossible to think about somehow winding all that back so that no trace of me being sitting here is somehow left in the universe. And this is this process by which you leave a trace in your environment is part of the idea of decoherence. And so the idea is you're losing, by leaving all these traces, the ability to sort of coherently interact these worlds together. That's called decoherence. And so that also helps decide how you think of potentially these worlds in the measurement process, is that they're ones which are kind of stable under that, so that they they are generally involving big things which have left a trace. And so we can then, at that point, effectively, in practice, if not in principle, we can kind of forget about the other worlds. Now, if you had sort of super alien powers in the many worlds interpretation, in principle, it should always be possible to interfere worlds together, however big objects they contain, but you need sort of unfeasible alien technologies to do it somehow. So in practice, we don't. I mean, that would be something I think that would convince more people that many worlds was right, though. If we could do an interference experiment with people, that would definitely be convincing. And people are trying to do interference experiments with bigger and bigger objects, with the idea that, at least in many worlds interpretations, this should keep working as far as we can tell, and it has kept working so far. Of course, we're a long way away from the scale of people.
Cool. So these problems of kind of figuring out the emergence of the worlds, there's kind of reasonable directions using decoherence in order to kind of see how these stable worlds emerge and kind of address this preferred basis problem of how these branches kind of effectively independently evolve.
But I mean, I think I'm a bit, so I'm not, I think some people in the sort of many worlds community would only ever use the word world to talk about these decohered, big, different on large scale kind of worlds. But I do find it helpful to use this sort of language when you even talk about things like interference experiments, so it's slits or quantum computers or things like that. I think it's a helpful way of thinking about quantum theory more generally. And actually that's kind of one of the things I like about the many worlds interpretation is it basically says the kind of things you see at the small scale, you know, try and understand them as best you can. And it seems to me that the best way to understand these often is at least to talk about stories about how they're really working and not just mathematics, is in terms of these sort of parallel world type ideas. And then to think, well, if those ideas seem to make sense for these small things, maybe they're also happening at the large scale. We just can't see them because it's much harder to do interference. And that idea of kind of, there's a simple set of laws and you should just keep expecting it to work unless there's some reason not to, is kind of at the heart of why I think it's a nice simple interpretation.
Yeah, cool. So yes, that leaves this kind of problem of probability, of figuring out why the probabilities follow that particular rule, the Born rule of quantum mechanics, which tells us how probabilities come about. So what kind of approaches have people taken to try and derive probability in the many worlds interpretation?
Yeah, so that's a good question. So there's been a lot of different approaches. So it's been a problem that people have thought about for a long time. So even in the original presentation of the many worlds interpretation by Everett, he had his own way of understanding probabilities in the theory. And then there have been a number of other approaches that are based on things like symmetry or entanglement or other things. Recently there's been quite a nice approach that Simon Saunders from Oxford has been pursuing about breaking the quantum state down into little sort of subworlds and then counting them in a sort of natural way. And then there's also recently been quite a lot of interest in an approach based on decision theory, which I'm going to say a little bit about. So that's mostly done by David Deutsch and David Wallace. And so their idea was, instead of trying to, because it's as we'll see in a minute, it's hard to even understand what you mean by probability in many worlds, really. So they say, well, one thing we use probability for is making decisions in cases of sort of uncertainty, and in particular in sort of deciding how to bet on games of chance and things like this. So what they imagine is, suppose you are a kind of rational agent who believe they're in the many worlds universe, and indeed they are, at least for the context of this thought exercise. How should they behave, and in particular, how should they kind of bet on the outcomes of quantum experiments in such a way that they're kind of rational? And they kind of proved that they should bet as if the outcomes were random and given by the normal probability rule that quantum theory predicts. So that was a kind of nice way of kind of giving something objective, of saying, how to think about probabilities in many worlds. And actually, I use some of the similar techniques that they use in their approach in my approach, but I have a slightly different starting point. So my worry about that is, firstly, they have some assumptions of what it means to be rational, which people have debated, and again, you could kind of question whether they're natural or not. Although they seem, quite appealing, but there's definitely been some debate in the literature about that. But also, it feels like it's not quite grasping with the problem that I want to grasp with. So in some sense, I think the thing for me that's the key question is, suppose we do live in many worlds, and we think many worlds is the right theory. How do we explain that actually in this particular world that I'm sitting in now, talking to you, there is a huge history of literature where people have tested quantum theory and found these exact probabilistic predictions. So it's like it already has been tested, and I want to explain why I find myself in a world in which the probabilities of actual experiments match the predictions of the traditional quantum theory to a very high degree of accuracy. And in some sense, that kind of question can't really address by decision theory, because decision theory is always forward-looking. It's like, what would I do next if someone gave me a game to play? Right? So it sort of feels like it's not quite the question I want to answer.
Right, because you want to explain the past results.
Yeah, I want to explain, on the face of it, you get this branching structure. I would expect there to be a copy of me that has seen every possible sequence of measurement results in some sense. But in fact, this particular one, those measurement results had a very particular pattern in them, in terms of the fraction of events which did a certain thing, and that was very well predicted by these rules which I threw away. So I've got to explain why that, Either I could just say, well, that's an amazing coincidence, so I'm lucky. But that feels a bit unsatisfying again, because I'd like a deeper explanation than that. So now I need an alternative way to kind of explain why that has happened. And that's not to say I don't think there would be copies of me who had seen very different results, and therefore maybe have rejected traditional quantum theory and gone down some other strange path. But the point is, I want to imagine that the experience I've had are kind of typical in some sense of copies of me, that I'm not an unusual copy of me.
Yeah.
There may well be copies of me that are experiencing bizarre worlds, but I want them to be sort of not too many of them in some sense. And that's the key, is sort of trying to evaluate that kind of sentence, what it means.
Yeah, could you expand on why the decision theory approach kind of says something about the future but not the past? Can you not think of these past results as the kind of outcomes of other rational bets?
I guess so. I mean, that isn't obviously what people actually did in them, but it also, I guess it's not, I guess my feeling is that they're telling you something about the world, not just about how you should act, if you're rational in the world. And I think it just feels that, if I understand why there are, in some sense, more of me that saw these certain results, then of course I'm very happy to bet on them. But I feel like that comes first, and the betting and the sort of reasoning about the future is kind of a secondary thing, slightly weaker thing. So it's still nice, and it's good because it kind of avoids the issue of talking about exactly what you mean by probability, because it is a very concrete sense of probability, and it makes perfect sense, like how would you bet in this situation? But I feel like it doesn't quite do that sort of fundamental thing that I'm hoping for somehow to explain the fundamental thing. So I think, and I guess there's also issues about exactly the assumptions and things like that, but like that's the main thing. So I think maybe I'll say a bit more about what my sense of because I've kind of been hedging around it a little bit, like how should you even understand the word probability in this many worlds interpretation, given that the theory is not probabilistic, right? So the way that I like to think about it is, so I suppose I believe there are these different copies of me that are all seeing different results. I want to say, suppose I could come up with a way of naturally, there's a lot of way going to be carried by that world, pick one copy of me at random in a kind of natural way. Suppose there was a way of doing that. So now I'm introducing something probabilistic. That's not part of physics, it's just part of me kind of just looking at one experience in this thing. So it's not like I pick it and imagine it's the only one that's real. All these ones are real, I'm just going to pick one at random from somehow ensemble of things in a natural way. And then if it's the case that when I do that, the vast majority of the time, I pick ones that see results of experiments close to what quantum theory has predicted, then that will mean that sort of typical copies of me believe in the rules of quantum theory as normally presented, and that would count for me as an explanation of why those rules were successful. Like that I should imagine I'm a typical copy of me in the sense of picking a copy of me at random in a natural way, and if it's the case that when you do that, you find the same probabilities or the same frequencies of measured results as we see in the real world, then that is kind of going to help explain the thing. And another way of thinking about it would be, so that's the way I prefer to think about it in terms of picking a copy of me at random, because it sort of very concretely puts probabilities into the game. The other way to think about it is just to think, I'm going to associate a kind of amount of each world in a natural way, a kind of measure over the worlds, which is like an amount of stuff. And I want that most of that amount of world is on worlds where the normal predictions of quantum theory were upheld, right? And it turns out that that's actually very similar because, in the end there, I can move back and forth between them, because if I have a way of picking the worlds that naturally with some probabilities, I can just think of that probability as the measure of that world, the amount of that world. Or conversely, if I have an amount of world, I can make the probability I pick that world proportional to that, and so they're very similar ideas, but you can pick whichever one appeals to you more. But that, I feel, was the game I was trying to do, to try and come up with this natural way of kind of picking a copy of me at random and seeing just to see what they experience, and then say, oh, most of the ones I pick like this see, that 3/4 of the spins are up, so therefore, and in fact, that is the prediction of the standard quantum theory, so that kind of makes sense. I think that's the idea.
Yeah.
And so that leaves. So that all sounds good, and that seems, maybe that's some progress. But of course, the devil is in the details, and the trick is in the natural way to pick copies of you, because you could come up with lots of different ways to pick a copy of you, and not all of them will agree with the predictions of quantum theory. So that was really what I worked on. I worked on, can I come up with what seems, to me at least, a compelling reason, a compelling natural way to pick copies of me, which recovers the right results. And so I've got my own set of kind of assumptions or axioms about how I should do this, and they lead me to what I hope is what's the result I wanted. But I think you'll see. I guess you can judge whether you think they're natural or not. So I tell you what my assumptions are.
Yeah.
Okay, so I have 3 different things I want this natural way of picking copies of me to obey, that I'm going to kind of think of as natural, like what I mean by natural. So the first one is, I want the probability of picking a particular world. So I talk really about picking worlds rather than picking copies of me, because it's a bit easier. But so I want to pick a world at natural, and then in those worlds, does the probability of the quantum theory obey? So my probability for picking a particular world, my first assumption is it just depends on the present quantum state of the universe. So the quantum state of the universe in many worlds is supposed to capture everything about the universe. And what this assumption means is that it doesn't depend on how you got there. So it doesn't intrinsically, if you know everything about the state of the universe, that's all you could know about that particular time. And so however I'm picking things, I should just care about that. And of course, the state of the universe will contain within it stuff about the history, but I'm not allowed to include extra bits about the history that aren't represented somewhere in the state. If the state doesn't know about it, I shouldn't use it. That seems, that seems pretty natural to me. Like that.
Yeah. So only things in the current quantum state is kind of information that you're allowed to use for this. Derivation.
Exactly. So. So that's the first assumption. So that hopefully, I think most people kind of assume that without maybe much discussion. The second thing is the first assumption, because I'm actually picking it from this date. So I have this date at this time, I'm picking a world at that time, I only care about the date at that time, not what it was last Tuesday. Okay, second assumption is, I think, probably the least controversial. So each world, so when you branch the quantum state into worlds in this way, each of them has a number associated with it, which is what we call amplitude. Now that number is actually a complex number in general, so that means it has a real part and what's known as an imaginary part, which is to do with the square root of -1. So -1 normally doesn't have a square root. You can't find a number that's squared, a normal number that squares to give -1, but you can invent one called I, and then you can combine those imaginary bits with real bits to get a complex number. And that's what quantum theory uses all the time. So this is definitely weird, but it's part of normal quantum theory, and everyone doing well. Okay, there's some interesting ways to get around it, but basically, in quantum theory, you generally use these complex numbers. The theory looks very natural, expressed in terms of them. That complex number, kind of, each of the worlds will have one of those kind of associated with it. And my second assumption is, if that complex number is literally 0 associated with that world, so in other words, if when you write the state in terms of worlds, that world doesn't appear, then you shouldn't assign any probability to it. So you shouldn't pick a world that somehow is not represented in the state. So in other words, if when you write this full quantum state of the universe out in terms of different worlds, some of them, some possible worlds will not be in that list. They're not part of that state. In that case, they also have no probability. I'm not going to pick them if they're not actually in the state.
So this is kind of like setting a boundary condition of...
Yeah, well, it's basically saying...
It must have 0 probability.
Yeah, I mean, basically, like you're taking the actual quantum state as the reality, and you're thinking of it as a branching structure of worlds. And yes, there may be, for a particular quantum state, there may be other worlds which you don't need to think about for this particular quantum state. Something else that just does not happen in this experiment at all, with no amplitude at all, with no probability. I mean, in principle, I could assign, regardless of what the quantum state is, that some particular world always has probability 1, even if it doesn't appear. That would be a very perverse thing to do.
Yeah.
And I want to rule out that. Or I could just ignore the state entirely and just associate, equal probability to every possible world or something like that. Although it's hard to count. There may be infinitely many of them, so that's another problem. But in general, it seems like I feel like this is the least controversial of my assumptions. I think the idea is when you express it in terms of worlds, you only need to care about the worlds you actually used in expressing it. You don't need to think about other possible worlds that didn't appear here. Now, maybe in some other experiment, those other worlds will appear and they'd be relevant. But for this particular state that doesn't have them in, 0 probability for them. So that's the second assumption. So far, I feel like they're both pretty compelling. Although, I guess people may differ. Then the third assumption is the one that does quite a lot of the work for me. So I'd say the first one is about, depending on the present state. The second one is about there being some weak connection to the actual amplitudes in the state. And the third one is to do with transformations. So this is what happens. So the idea is that when you transform the quantum state, when it experiences some evolution via the Schrödinger equation, because that's the only type of evolution we have in our new worlds interpretation, then that must be reflected a little bit in how the probabilities change. So the idea is that the probabilities are somehow connected when the system undergoes the evolution to how the state evolves. And the way that I present this in the paper that I wrote is, if you can divide the worlds up into groups, and the way that they evolve is each group evolves completely separately, so that the worlds in this group never transform into the worlds in the other group and vice versa, then the total probability of each group is preserved. So in other words, the probabilities can't flow between worlds that are not coupled by the actual dynamics of the system. So when you do an evolution, if these worlds sort of transform into each other and these worlds transform into each other, but there's no kind of crosstalk, then although the properties might muddle up inside this set and they might muddle up inside this set, you shouldn't suddenly get sort of probability jumping from one set to the other, because that kind of wouldn't be natural. Yes, that's the idea.
Yeah, so if the worlds don't interact at all, then you could kind of add up their probabilities as these. You draw these lines of which worlds interact, and that gives you your groups, and then you say all of those have to add up to one. These kind of
well, crucially, each group, its total has to be constant. If those act as a group for that particular dynamics.
Yeah.
In that particular transformation where they are acting as a group, the total of all the properties only moving between them, not out of that group. I mean, there's actually, I realised subsequently, actually this was in a conversation with Simon Saunders, who I mentioned earlier, that actually I can even get a slightly simpler version of this assumption which does the same job. It turns out I can prove the same things with this slightly simpler assumption, which is just all I really need to assume is that if there are some worlds which are completely unchanged by the dynamics, so in other words, those worlds stay exactly the same and no other worlds transform into them, so they're essentially just left unchanged by the dynamics, then the probability of those worlds that are left unchanged has to be conserved. That turns out to be just as powerful to do what I want.
Right. And does it have to be the case that those worlds actually happen in a way, or just that you can conceive of a world that is left unchanged?
So the clever thing about this, the first assumption I make is, so I just assume that in these particular cases where, just in case you manage to do an evolution where this was unchanged, this one doesn't, it would behave like this. It turns out that's strong enough to prove the properties for all kind of scenarios, because I have this dependence only on the state and not how you got there.
Yeah.
If I can come up with one way of getting there where everything is nice and simple,
and
I can prove the properties work for that, then I've kind of done the job, and however else I get there, it will turn out to be okay. So I only need to assume that things work nicely for the cases I'm going to use to construct the probability rule. And then later, I guess I do need to go back and double check that the probability rule makes sense in every other circumstance, but it turns out it does. So although these evolutions where things, these ones stay exactly unchanged and these ones change exactly into that, they're hard to imagine doing in practice. But in the theory, they kind of exist. So I'm going to allow myself to prove this theorem to make potential use of any possible allowed quantum evolution. But of course, all I need to do is establish one sort of sequence of evolutions that proves the properties are what they sort of expected to be, and then then I've proved it. And so it, in every other case, something more complicated might happen, but I can then use the probability rule to work out how it works.
Right.
And it turns out that these three assumptions are enough by a sequence of kind of transformations that the only possibility that satisfies them all is the normal quantum prediction, so that you can recover the normal quantum prediction. That's the idea.
So you kind of consider these this kind of conservation law in a way of the probabilities remaining constant in these subsets, and then using your other assumptions, you can kind of extend the conclusions you draw from that to kind of any evolution that can happen. And then since you can kind of get the probabilities emerging in the correct way with these groups, you can then extend that to getting them emerging in any situation.
I guess the point is I need a natural probability rule. So I need to pick the world probabilities from this data in a natural way. And that natural way has to work for every possible sequence of things I could do. And so if I can think of a particular way of kind of building that state, which leads to the probabilities that I want, then if that's the only way to do it for that sequence of transformations, then they are the properties associated with that state, and it doesn't matter how it got there. So any other way to build it would give you the same properties, because it's just a property of the state. So that was why it's important that the properties don't depend on the history, basically, because once you've associated a natural way to a state, you can then forget about how you particularly proved it, and that is the thing. And again, it's important to go back and double check, because I guess I've just proven that for this particular sequence, this is a natural thing. There might be another sequence where that's unnatural, and then it would be wrong. But because these are the actual, the normal predictions of quantum theory that I'm recovering, actually it turns out they're also natural for every other sequence. They're never going to violate these rules, that you can convince yourself that. I mean, normal quantum theory does obey this thing that if you take a set of states and evolve them separately, and another set of states and evolve them separately, then the properties of each group is conserved. So it does kind of obey the axioms. But I need to kind of prove that myself, because I'm going to prove that works, and then kind of check it works for everything else, and it does, because it's all quantum, and then I've done. So the idea would be basically, if you believe that this whole way of thinking about property makes sense, and if you think that these are reasonable properties that a natural probability rule should obey, then essentially it solves the problem of where do the properties come from in many worlds.
Yeah, I think I understand now what you meant with the history aspect, is that you look at a particular conceivable history for how you can get to that state that has this nice property, and then because you can conclude the probabilities for any history, you can then say, okay, whatever history actually happened would also have these probabilities.
Yeah, and actually it sometimes goes the other way, actually. So what I tend to do actually is that I start with the state that I want to explain the probabilities of, and then I evolve it into something else which I can easily calculate the probabilities for, and then I kind of retrodict how those properties kind of come back to the thing. So it's kind of, so the idea, so a simple example would be, essentially if you've got two worlds, but one of them has a sort of bigger amplitude than the other, and we know the correct thing to do is associate more probability with the one with the bigger amplitude, but it's hard to just do that without a good reason, because maybe these amplitudes are just irrelevant to probabilities. So what I can do in that case, suppose what you could find out is that suppose it's the case that you could do some quantum evolution that branched the one with the bigger amplitude into two equal worlds. And then all three things would have the same amplitude. So you start off with one with a big amplitude and one with a smaller amplitude. And you do an evolution where this one stays completely unchanged and this one branches into two equal things.
Yeah.
And then these all have the equal amplitude. Then what I want to show, I also managed to show that if things have equal amplitude, they have the same you should associate the same property with them using the rules. And then because these two branches came from this branch and this one was left unchanged, I can use my third rule to say, well, the total property of those must equal the original property. So I kind of pull them back to the original state.
Right.
So so you kind of want to maneuver the state you've got into something you can understand more easily.
Yeah.
Via a sequence of steps, and then you sort of, okay, I understand how to do properties for this, and I can kind of pull them back to the original state. And so the sort of key elements are firstly proving that if you have two worlds with the same amplitudes, that they should have the same probability. And actually you do this by sort of sequence of kind of swap type operations. So it's a little bit, you can't, maybe it's not worth going through the full details of that, but I can do it if you want.
Kind of the idea of that you swap them and then you say it has to be invariant even if you swap
so basically,
them,
the way you actually do it is you think of those two worlds with this amplitude and a sort of third one that has originally zero amplitude. So you imagine some hypothetical world that you haven't created yet. So you start with just these two and this one that's empty, as it were. And because by my second rule, this one that has no amplitude has zero probability originally, so the property must be across both these ones somehow. And then you want to sort of swap these two around, but only interacting with one of them at a time. So what you do is you swap one of these worlds with the empty one, okay, and that you can do. And then because, so now this one is empty and this one has some probability in, but because this one was left unchanged, all the property that was already here must have moved here.
Yeah.
And then you can swap this other one with the empty one. And again, here this one's unchanged, so its property has to stay constant. And this one swaps with this one. So, and at the end, this one started with zero amplitude, this one ended with zero amplitude, so they must have zero property, so all the property must go from here to here. And then you can do a third swap where you pull this third one back into the first place. And you've essentially swapped the worlds. You do a sequence of three swaps with one empty world and two kind of equal amplitude worlds. And you end up swapping the two worlds you care about and putting the zero one back in the zero thing at the end. And because each step you're always moving the probability from one to the other, you can show that under this process the property must have switched. It kind of just moved with the swaps. And because the state at the end is the same as the state was at the beginning, because it turned out originally things had equal amplitude, at the end they've got equal amplitude. And because all you care about is the state, that is the same state. So nothing has changed in the state, but the probabilities have switched. The only way that can be true is if the probabilities are the same. So it's a kind of slightly convoluted thing, but it is, you could. I think that would have been easier if I'd drawn it, but they won't. So that's one element, is proving that things with the same amplitude, sort of amount of that thing, of that world, those had the same sort of number in front of it, they have the same probability. And that's something you might have imagined anyway. Like, seems very natural, but it was at least impossible. It was at least plausible that you should associate probabilities based on some property of the world. Like, does it have, I don't know, more energy or bigger people or something? I don't know. Like, you could imagine some crazy rule. And this rules out, it says, the only thing that matters to the probability is these numbers. If these numbers are the same probability. And then the way you extend it to other more complicated situations, you say, well, if you have, if you can do this branching where you can, what you ultimately end up doing is trying to split some things, all with different amounts of them, into lots of copies of things, all with the same amplitude. And then you can count them, basically. So that's basically the strategy. And it gets a bit fiddly when the amplitudes, these numbers that are associated with, well, if those things can be written nicely in terms of fractions, it's quite nice. If they can't be written nicely in terms of fractions, you have to do some bit more complicated shenanigans to get this to work, but it essentially all comes out.
Cool. So, and then do you find this kind of a fully satisfying, compelling
I mean,
derivation of probability?
basically, yes. I mean, I'm pretty happy now, so I want to stop working on it. But, I mean, there are other things you might have wanted to include. So at the moment, I haven't included locality at all, particularly. Like, I don't really use the fact that maybe these things have different places in space, and maybe I could have used that. But to be honest, for me, the assumptions all seem pretty simple, so it's hard to think how easy it would be to get something even simpler that would still work. So this has made me pretty happy. So, I mean, the other thing I did in the paper actually, which is kind of, I find kind of, for me was a bit appealing, was I also, as I didn't really want this whole idea to be too fine-tuned to quantum theory. Like I didn't want the assumptions to kind of somehow have a hidden understanding of quantum theory in them. So I actually applied this as well to other sort of toy many-world theories, which are not quantum many-worlds. And it gave reasonable results for them. So this is kind of a bit reassuring because it means that, in some sense, those, again, it sort of means they are kind of natural in some sense, these assumptions. So a particular one thing I looked at was you can essentially think about a theory which is made up of kind of classical probabilities where people, each step the system has some chance of being in particular things, and then, when it updates, you roll dice and see where it goes and that kind of thing. Like you can imagine kind of writing that thing down as a theory. Classical probabilistic theory. And actually these things are quite hard to understand. Like if you try to think about an intrinsically classically probabilistic world, it sounds like something, as someone who plays quite a lot of games, it sounds like something that seems to make sense to me. Like, that board game is almost this, right?
Yeah.
But of course, in some sense, it's a bit different because in a board game, when you roll a dice, if you really knew the precise position of the dice, the precise position of a hand and stuff like that, potentially you could predict exactly what it would be. So it's more ignorance rather than actual kind of randomness in some sense. And so trying to understand what actual randomness is actually quite hard. It turns out it's actually quite hard to understand what probability is, what objective probability means. We understand very well the idea of probability is kind of ignorance of some unknown thing, but thinking about something that is intrinsically just random as a process is quite hard. And one of the reasons it's quite hard is that one of the ways we kind of think about probabilities in terms of frequencies, like if I rolled a normal dice a lot of times, I'd expect to get roughly, a sixth of the time, I'd expect to get one in a large number of trials. But actually, if you think about it carefully, what you really ought to say is, if I rolled the dice a large number of times, I would expect to get one about a sixth of the time with high probability. It's kind of circular. So it's actually quite hard to formally define it in a way that's completely satisfying. And so mathematically you can say, well, if I rolled it an infinite number of times, I would get exactly a sixth. But the problem is, of course, no one's ever rolled a dice an infinite number of times. So there's an actually long-standing problem in the foundations of probability, which is we don't really understand what objective probability is. So one of the things I thought about is actually I could flip this whole thing on its head and say, actually, maybe what the one way to understand objective classical probability is, it explains what it would be like. It's like what it would be like to live in a many worlds theory based on classical probability theory. So where, the classical state is a branch state of different possibilities with different amplitudes associated to them. Now it happens that in the classical many worlds theory, those amplitudes are just normal real numbers that sum to one and are positive. But mathematically, it's actually described by a very similar non-classical structure to our many worlds theory. And so I can apply my same rules. So suppose we were living in this structure which looked like a kind of many worlds version of classical probability theory. What's the natural way of picking the probabilities for the worlds? And it turns out it's the probability. So it kind of recovers. It's a slightly offbeat attack on the question of what is objective classical probability. And I could say one thing you can think about it is it explains it's like what it is to live in a classical version of many worlds theory, basically. The thing you would expect, that would, in some sense, have, it would feel probabilistic to live in that, and the natural probabilities that come out would be the ones that are baked into the theory as the kind of amplitudes of the world. But, okay, that's maybe a bit, but it's not, the main motivation for me was definitely thinking about quantum many worlds, but I guess it was
Yeah.
kind of reassuring that was kind of what I would hope that my theory would tell me. If I've sort of hidden classical probability theory in this many world structure, it finds it and kind of gives you the right answer.
Yeah. So the idea of this classical many world setting is that you kind of in a universe that somehow had fundamental classical probability, you can again recover it from a similar set of assumptions.
And I guess it's more like this is a many worlds theory which somehow, in some sense, is deterministic, but the experience of living in it would be like living in some sense a classical, fundamentally probabilistic kind of experience somehow. Like I think that would be the...
Yeah, and you can make sense of probability in that setting.
I think so, but I mean, okay, I don't want to lean too hard on this because maybe that's not more appealing than the other approaches to classical probability theory. I mean, in many worlds quantum theory, we have other reasons to worry about these parallel worlds in classical theory, like people aren't really. But it is surprising, I think, to most people that we don't have a good handle on what it means to have objective probability really in physics.
Yeah. Cool. And I'm curious how, in your kind of process of working on this, how did you end up settling on these three assumptions and kind of
it's a good question.
Getting the result in a way? What was the process?
I think I just thought about it a long time and just tried to come up with something as simple as I could that got the results. Actually, some of the approaches, so I mean, again, and also borrowing things from like conversations with people or reading other papers and things like that. So in particular, this strategy in my paper of branching the things into in order to get worlds with equal amplitude and then trying to prove that worlds with equal amplitude have the same probability, that's very much the strategy adopted in this decision theory approach. So actually the papers that the Deutsch-Wallace kind of papers about decision theory, they really helped to solidify a strategy for doing this. And I guess I was like, I like this idea of the branching, but I'm not so sure about the sort of thinking about it in terms of decision theory. Can I do something which is sort of similar mathematically but is a different conceptual kind of foundation? So I guess that helped.
And then you found this kind of simpler set of assumptions that by a similar strategy for part of it kind of led to the right outcome.
And I was also interested in probability flows in general in quantum things. So, this idea that, how do, when you've got something that's evolving via some dynamics, so you've got some initial state and you set it properties with that, and then you evolve it via some finite amount of time by the Schrödinger equation, you get some new state with some probabilities associated with that. You kind of want that the probabilities kind of flow from the initial state to the final state in a way that respects the dynamics. And actually I've been working on a problem of whether that, whether it's always possible to do that in a way that's kind of, those flows kind of work nicely with respect to dynamics in discrete time sort of evolution systems. So if you've got some, so people have looked a lot at probability flows when time is kind of continuous, there's sort of probability currents. But if you imagine that time sort of is in discrete steps, so you get a finite amount of time and the thing updates and a finite time, a bit like a quantum computer often works like the sort of gates that acts in finite times. It wasn't so clear then that you could understand the probability flows in that kind of scenario, and that's one thing I'd want to talk about, kind of fed into this a bit as well.
So you were thinking about how to translate the probability flow behavior from the continuous time to the discrete time setting kind of separately, and that got you thinking of probability flows and that kind of assumption about the natural behavior of probability flows.
Yeah, so I mean, I think another way to get my result, the third assumption, which I already have two versions of, I actually have a third version of in the paper, which is you could imagine that you need there to be some probability flow from the initial state to the final state. And, basically, if you just assume that the probability flow is 0 if the dynamics doesn't directly. So the way you explain these dynamics is each world in the initial state has some amplitude to go to each possible world in the final state. Basically, that's the sort of way you pick up a dynamics. If that particular transition amplitude is 0, in fact, so if the dynamics that you're considering over this particular time has no amplitude for this particular state to go to this particular final state, then you shouldn't allow any probability to flow between them. Right. So the idea, if you impose that rule that the probability flows have to kind of mimic the things that are connected by the dynamics, which is a bit like the flavour of the other things I've said, but this would be at the level of each individual world, like how it moves. That also is enough to prove the theorem, and that was also what I wanted to show in this discrete time.
Right. And are these types of assumptions, so earlier you kind of mentioned locality, can you think of these as being related to locality in a sense of only if you kind of locally interact can the probability
interact?
I mean,
so it is true. So many worlds is kind of interesting in its sort of status with locality. So it is true that if you have, in many worlds, it's kind of more friendly with locality than traditional kind of measurement models. So normal measurement models, when you do a measurement, you kind of collapse the state everywhere in the universe, and that feels very not local. Like if you do a measurement over here, the whole state of the universe collapses. In many worlds, it's not like that. If you have two different regions, essentially each region kind of separately interacts with the local measuring device. And in fact, sort of, you have two quantum systems here and here, and this one's interacting with this measuring device, and this one's interacting with that measuring device, and there's no kind of, in the dynamics, it's very local. So that's kind of a nice way. I guess the only thing is that the quantum state itself is not a local object in the sense that you can't describe the quantum state by describing this bit separately and this bit separately and this bit separately. And this is to do with entanglement between systems. But the probability flows, actually, they're a bit more weird, actually. So the way the probability flows move could depend on things that are happening in different regions. And this is, if this was not the case, then you would, so this is a whole nother topic probably, but this is related to quantum non-locality and Bell's theorem, which says that there are correlations that you can get in quantum theory that cannot be explained by any local classical probabilistic model. And I guess if it was true that probabilities were kind of defined locally and only flowed locally, that would be precisely one of these classical probabilistic models. And so there is some interesting behavior happening in the probability flows for entangled, complicated quantum structures, but it's not something I look at particularly in this paper.
Cool. You've said that you find this derivation quite satisfying. Just generally from like talking to others in the scientific community, what do you find is kind of convincing for other people, or they have a kind of different
yeah, that's a good question. I guess I've definitely had some people react positively to it, but I think a lot of people in the community are kind of developing their own things that make them happy about, in terms of making this. And I guess there's no consensus at the moment as to sort of a unique way to do this. I mean, in some sense, I think that's kind of healthy, right? Because we are in a slightly, philosophically, like there's no, you're talking about sort of things that seem reasonable to you, and like how should you think about probability in these? Like we just don't have a lot of good ways of thinking about what it would be like to live in a multiverse, a branching multiverse. Like, so I think actually it's quite helpful that people have different approaches and they all kind of build this picture of why this is a natural way to understand probability, or that at least we shouldn't be too surprised that we recover the probabilistic part of quantum theory, that there are sort of various different ways in which it's very natural given the structure of the theory. And I think these different approaches kind of highlight different bits of that, and address slightly different problems, like this idea of thinking of probability in terms of rational action versus thinking about it about kind of explaining historical records versus thinking about it in terms of what's natural and what's not natural. Again, like maybe other people find their own, assumptions more natural than mine, and that's completely fine. And I think that, but I think that it generally is something where, I think one issue is people sometimes say, well, look, this whole many worlds community, there's lots of different versions of many worlds, and therefore they're not even deciding among themselves, so why should I kind of buy in? And I think that's a bit misleading, because ultimately everyone really agrees that the basic idea is there's just the quantum state evolving via the Schrodinger equation, and everything else is just what it's like to live in that mathematical structure, and does it is what it's like to live in that mathematical structure like what it's like to live in our world? If it is, it's a pretty nice simple model. If it's not, then hopefully at some point you get some counter argument that was strong, but we haven't found one. As far as all these approaches have seen, it seems to be that it might very well be that living in this mathematical structure was like living in our world, and we can explain the kind of phenomena we see. And so I think and people have slightly different focuses in terms of focusing on thinking about decoherence of the worlds, and how quickly that happens, how stable that is, thinking about particular ways to think about probability, how to even conceptually what is it you're trying to talk about, and then how to get the Born rule, how to get this traditional quantum probability rule out. But I feel like they're all kind of working in the same direction. I don't think there's any real disagreements. Sometimes people might use language in a slightly different way as well, because they find that helpful. But I think the key to emphasize is the mathematical idea of theory is really the same for all of us, and the basic predictions are all the same. It's some of these details about how exactly you talk about it which people are still kind of coming up with their own understanding of, and I think at the moment that's quite kind of a positive thing. And but I guess from a sort of presentational point of view, sometimes feel like it's less maybe that will make it easier to sell to other people if we arrive on a kind of canonical picture. I think it'd be a bit less satisfying for the individuals involved. And I guess a lot of people rightly, a lot of people take the view, of course, particularly if they're working more applied things, of well, I know very well the rules of quantum theory, they seem to work incredibly well, I'm just not going to worry about them too much. And that's a pretty reasonable attitude to have if you're mostly interested in kind of practical effects and building machines and doing these kind of things. Personally, I'd find that completely unsatisfying. I always want to understand things at the deepest level, understand why they're the way they are, and trying to see what does this theory really tell us about the universe and our place in it. And I think I wouldn't, the idea, there's a famous quote of, is it from Feynman, shut up and calculate? I don't find that very compelling as a kind of strategy myself. I like to at least try and attack these big questions and understand what's going on.
Yeah, it kind of just leaves the question unanswered, to the side.
And it's important to recognise, though, that a lot of these issues, we have tested quantum theory incredibly well, and the rules we learn that involve these two different parts, they work incredibly well. So it's really is a more philosophical. There are no experiments at the moment which would help to distinguish these issues. Now, if you do interference with bigger and bigger things, maybe at some point some of these things like to be slightly different. Like if there was sort of objective collapse, maybe at some point you start seeing that. But in general, it is more about trying to understand the nature of the universe, for me at least. And of course, the other possibility, which is another recent one, is that maybe quantum theory is not the end of the story. If historically, people thought that classical mechanics was pretty much the thing, and there was only a few minor details to iron out, and then we had this massive revolution to quantum theory. So it's possible that there will be some future theory that is quite different in many regards to quantum theory, and in that case, of course, maybe that will reopen all these questions. But in as much as quantum theory is right, at the moment, it feels to me like this is the right way to understand it, and I've been, who knows, maybe I'll change my mind, but at the moment that feels like a good conclusion. And hopefully, maybe more people out there will gradually move in. It feels like the direction of travel is slightly towards many worlds. I don't know if you get that sense.
I have heard people becoming convinced of it after hearing the arguments towards it. I'm just curious, did you switch to it from preferring a different interpretation in the past, or you kind of from hearing about it, you found it compelling?
Yeah, I think as soon as I started really thinking about the problem, it was, I think I was always inclined to go down that path, because it is in some ways just the simplest thing. Like, if the issue is you're treating measurements in a weird special way, stop treating them in a weird special way and see what happens.
Yeah.
And if it turns out that then what you get back is what you're expecting anyway, then that sort of feels like that's going to be a good solution. And a lot of the other approaches to the measurement problem in general, I guess we haven't talked too much about them, but they have elements which seem, more ad hoc to me, like in some ways. So,
yeah.
I mean, there is some interesting recent work about a way to combine kind of classical gravity with quantum theory, which kind of maybe that's a bit less ad hoc, and maybe that. I mean, I'm still like at the moment not convinced, but it kind of is interesting in this case.
Yeah, cool. Yes, I think we've covered a lot, and I can just try and kind of summarize what we've talked about. And so we started with the measurement problem of quantum mechanics leaves unexplained the difference between the normal Schrödinger equation evolution of matter and then this measurement rules that describe measurement processes. And a way of kind of reconciling those two different behaviors is the many worlds interpretation, where you say that the Schrödinger equation evolution actually applies everywhere, including to the measurement devices. That leads to this branching of measurement devices into different branches that we kind of refer to as worlds, which is this many worlds interpretation. And then there's a few things that need to be explained in that picture. One is kind of the emergence of these worlds and how you kind of characterize them, and we discussed how decoherence is a way of kind of seeing how they emerge. And then another aspect is deriving why the rules of probability emerge the way that they do when you make measurements. And you gave some intuition of why you'd expect that you can see randomness as you progress through these branches, but then you also want to explain why the probability rule is the way it is. And then you mentioned that there's various approaches to deriving probabilities, including one from decision theory of thinking about how a rational agent would bet on measurement outcomes, and that kind of leads to the right probabilities coming out. But you found some of those assumptions not satisfying for kind of the question that you want to address, which also includes the kind of past history of why the outcomes came to be as they were, and kind of try and remove the idea of having to define a rational agent from the derivation. So then in your approach, you've got these three assumptions that seem natural from which you derive the probabilities. One of them is the...
a good test here.
Yeah. Yeah, let's see if I remember the three. One is the state is the present state is the only part that matters.
Yep.
The second is that if you have a world that has zero, that does not appear in your state, then it has zero probability. And the third is that if parts of the state, if these branches don't interact, then the probabilities are independent, so they remain overall constant in regions that don't interact of the branches.
Brilliant. Yeah.
And from these assumptions, you can then use a similar type of proof to the decision theory approach in order to derive the probabilities, and they come out in the right way that we have in actual quantum mechanics.
Yeah.
Cool. So, are there any kind of final words you want to leave the audience with, or final comments on this topic?
Yeah, I guess I do encourage people, particularly people who kind of are interested in studying quantum theory. So when you study it, you have to learn a lot of maths, and that's really important to really understand what's going on. But it is worth spending some time thinking about what you think it should say about them. Don't be a person who just says shut up and calculate. Just try and understand what it's saying about the universe and have some time thinking about it and explore some of these different options and see if you kind of are convinced. And of course it is a pretty radical thing to kind of accept that there might be parallel worlds with different copies of you and experiencing different things, but physics has got a lot of interesting things in it. Maybe there are other radical things. But I think, just encourage people to not shut up and calculate. I think but to do calculations, it's important to understand the maths as well, but to also just think about, the fundamental nature of reality. So.
Yeah, great. Well, thanks for coming on the podcast and explaining this research. Brilliant. And I'll see you next time on the Quantum Foundations podcast.
Thanks very much.
Bye.
Bye.